Awesome. Welcome, everyone. Today, we are going to learn about financial semantic search and re-ranking using Cohere and Pinecone with, of course, myself, Arjun Patel, and Jan from Cohere. The agenda for today is we're going to learn about semantic search. We will showcase how to use Pinecone with our new feature, integrated inference. Jan will talk about Cohere's new re-ranking model, Rerank 3.5. And of course, any webinar would not be complete without a demo. So we'll showcase an example notebook showing how to use integrated inference in Cohere 3.5 on a financial data set. And finally, we'll end with QA around the 45-minute mark. This is myself. I'm Arjun. I'm a developer advocate at Pinecone, and it is my passion to help people learn about how to utilize vector databases and build really cool AI applications. So I'm pretty excited today to talk about how to implement re-ranking and do advanced forms of semantic search. I'm here with my buddy Jan.
Yeah, Jan Stoneman, Staff Solutions Architect at Cohere, and it is my passion to help with AI models from the full stack, which I'll be talking about, and building AI applications with them. It's been really fun to combine that with Arjun's passion over the past few days building out the demo, which I'm looking forward to showing you.
Before we motivate why you should care about implementing semantic search in a specific expert domain, it's important to talk about the limitations of current techniques like keyword search. You can only use keyword search to help you find things that have significant query overlap over the questions that you're asking, and that can only take you so far. A lot of the times, you need to go beyond what is written inside your query to what your query is trying to represent. There are two key things that keyword search doesn't do so great with. The first is understanding the meaning of the queries you're trying to use. For example, you might not know the exact keywords you should be looking for when searching over technical documentation. Or maybe you're working for a multilingual corpus and you're querying in one language and needing the results to return in another. In addition to that, keyword search doesn't handle conceptual searching very well. So if you know the kind of idea or thing you're looking for, but you don't know exactly what those documents contain, keyword search is not going to help you with that. This is also helpful for where you have asymmetric forms of search. So when you are asking a question and you're trying to return a set of documents that can answer that question, keyword search can kind of fail at that too. This is why semantic search can come in really handy. What semantic search enables is representing the meaning of any given query within vectors. What you need to do, and before you're able to implement semantic search, is to represent your input queries as numerical values, which we're referring to vectors in this first document here, or first image here. We then take those query vectors and we compare them to document vectors that already exist inside some sort of data store, in this case a vector database, and we determine how relevant those documents are to the input query based on their closeness in vector space. We can see in the bottom right diagram, we have a bunch of query questions like when were the Normans in Normandy, and we have documents that are clustering close together in this hypothetical vector space that allow us to answer that question. Of course, speaking of questions, this kind of begs the question of how do we actually represent these documents in a way that allows us to do this kind of search? Well, we use embedding models to convert these types of words and sentences to vectors. And embedding models consist of neural networks that are trained on tons and tons of data from all across the internet, which end up learning relationships between the words inside a given document. And those relationships are encoded in the vectors as meaning. Because they're encoded in this fashion, we can perform computation on those vectors in order to determine what is close together in meaning and what is far away. Now that we have a way of converting queries into vectors, and we have a way of understanding how to do search amongst those vectors, we need a way of storing the document vectors so that we can do that search really quickly. And that's what the Pinecone vector database allows you to do. You can pass an input query to Pinecone, it'll go through an embedding model, and you'll be able to efficiently and quickly search hundreds of thousands to millions of data points inside vector space to find the closest set of documents that you need. Pinecone is able to do this because of how it's implemented. You can use Pinecone in a serverless fashion, which separates the compute and storage costs, which means as your query load increases, Pinecone will scale up. As the amount of data you're upserving increases, Pinecone will scale up without you having to provision these independently. So when you implement this type of architecture with Pinecone, it's going to look something like this. And this is what we're referring to as a semantic search application. You'll have your data source, which might have associated metadata, and you'll also need an embedding model, which will let you convert the queries into embeddings, especially when you're upserting into the vector database. That'll get sent to our API, which interacts with the Pinecone vector database. You pass in your query, you get those results back, and those are your semantic search results. But what's difficult about this type of architecture is that there are a lot of moving parts that you might need to set up. For example, you might need to host or deploy an embedding model. You might need to handle how data is being upserted. You'll need to handle how data is being chunked. And of course, you'll need to coordinate all of these if you have lots of different places or entities upserting or querying data. With the release of integrated inference, there's now only one API call needed to do embedding and upsertion with Pinecone, whereas previously you'd have to embed the data yourself with one API call and then upsert it again with a different one. You can pass text into the endpoint, it will get embedded and upserted into Pinecone, and then you can query with text again directly, which greatly simplifies this workload of semantic search. It's also faster because we're hosting state-of-the-art deployed models on our infrastructure near where the vector database is located. And we've already picked really good models for you. We're going to talk about one of those models today in reranking with the Cohere reranker. What does this look like? When you're managing an index, all you have to do is specify the model you want to use, which that index is being created for, inside the creation of the index call, which makes it super easy for you to not only create the index, but specify what the dimension size should be and set it up for the following requests. After you do that, upserting and embedding the data requires only one line of code, specifying your namespace and the records you're trying to upsert. Then, when you want to search, you no longer need to do a separate rerank call as well. You can specify your reranker, as we've done here with Cohere rerank 3.5, in addition to the input query text and some other hyperparameters to ensure that your results are relevant to what you're interested in to get your hits back. This is extremely handy and avoids making at least 2 or 3 additional API calls. This will be what we will demonstrate today inside the notebook. However, when we implement normal semantic search, there's a problem. There's actually a lot of use cases in which semantic search is not enough. And this happens when you have 2 specific things. You might need further refinement of the results that are being returned by your initial semantic search. Typically, when you work in a domain where you need a really specific definition of what is relevant or what isn't relevant, or there is a premium placed on the number of documents that should be sent to some downstream review process, we refer to this as context optimization, then you probably need to do some additional cleaning up of results that are being returned by semantic search in order to make this pipeline work. A reranker is another model that can help you refine this initial set of returned documents from semantic search in order to make your results as relevant as possible. So when we talk about relevance, what a reranker does is it takes in an input user query and a document and computes a pairwise score, which is contextual of the input user query and the return document. Then, once you take all of these scores, you re-rank them by highest score to lowest, and you return the subset of the most highly scoring documents, which means you're returning less documents that are more relevant to some downstream process. And because the re-ranker takes into account the document and the user query at the same time, uniquely to each user query and document pair, the scores are going to be specified with those in context. So you know that the documents being returned are the most relevant for your given workflow. Secondly, there's this idea of context optimization. When you're working with semantic search within some other larger architecture in which you need to pass the chunks off to a human reviewer, or you need to pass the chunks to a large language model, which we aren't covering today, but it's useful to think about, you can approach this task as a context optimization problem. If you have too much context, that can eat up a lot of important time that your reviewer or your LLM is trying to use to find the important piece of information. If you have too little context, you might miss a document that actually is critical for you to complete some downstream task. But if you use a reranker, you can optimize your context to ensure that at least the documents you're returning are the most relevant for whatever downstream process you're trying to implement. And in the case of an LLM, you can decrease cost because you're using less documents inside the prompt for your retrieval augmented generation workflow. But enough from me about what re-ranking does. I'd like to pass it over to Jan so that he can tell you about the strengths of the Cohere 3.5 re-rank endpoint. Here you go, Jan.
All right. So rerank 3.5, we've talked about why we want a re-ranker, but now let's talk about the state of the art in re-ranking. We released this in December, and let's talk about some of the significant new capabilities we can do with this re-ranker. So now it's one model that performs better at all of the languages, and we have an a huge improvement in complex reasoning tasks because basically before this model, no models were able to do this. And we'll talk more about what benchmarks are used here in coming slides. And then there's the same SDK as before, so you can just update directly to Rerank 3.5 if you've been using it before. So here's an example of what I mean by complex reasoning. So let's look at this example query. I'm looking for a place to stay in New York that's not in Midtown. So Midtown is what the lexical search results are grabbing onto here and giving you in the top one result. But I'm asking for not in Midtown. And negation has traditionally been hard in all types of language models, including re-rankers. But as you can see, the re-ranked results are not giving you anything from Midtown. But it can also do multiple steps of reasoning like that. So under $300 a night, as you can see, the lexical search here is latching on to 300 and giving you $3,000 a night, very off from what you want. And you can see the first two results are under $300 a night on the re-ranked results, and the third one is not too much higher. But you can have yet another step in the reasoning. So 3.5 stars or higher. And you can see the first result on the lexical takes the 5 from the 3.5. The second result takes the 3 from the 3.5. Whereas the right side is understanding 3.5 or higher. So it's purposefully giving you something higher. A regular semantic search might just give you 3.5 on the right side. And you can also imagine entering this exact query in Spanish, for example, and getting still the same results because it's semantic understanding and with multilingual support. And let's look at where this fits in the context of Cohere's stack. So we also offer generative models, and we just released a 7B model a month ago, and embedding models, and Rerank 3.5 came out in December. So in the full stack of LLM you need to do AI applications. The embed, we also recently released multimodal support. And we're talking mainly about search, but you know, you can, once you add on the generative at the end, you call it a RAG. So let's go one forward here. Yeah. And if you're looking for that orange dot in a document with embeddings, you'll want to measure the distance. Let's click one more forward. One more, yeah. And it'll find which ones are within a certain range, but then you take those and then you can do more fine-grained search on it afterwards and get more exact scores. Next. So let's talk about benchmarks. So I saw a question about what benchmarks are used here. So this is actually based on an internal benchmark we have based on customer feedback of what our customers care about. And we saw this huge jump and reasoning capabilities from our previous model, Cohere Rerank 3 to Rerank 3.5. And that's because this type of reasoning that I showed with the hotel example, it wasn't supported for the most part, like things like negation and um, date understanding and so forth. Um, and yeah, let's look at the finance benchmark. So what this translates into for finance is when you have uh, understanding of dates and numbers and actually reasoning over those numbers. Of course, that's great for financial documents like 10Ks. And here we are using like Finance Bench and other benchmarks to show you the difference. And Q&A on SEC filings, you can see a big jump there. And yep, let's keep going. So here you can just see this is the full list of improved performance. And one thing to point out for those of you who used Rerank 3 in the past, better score normalization is one of my favorite little quality of life improvements here with Rerank 3.5. Previously, you could mainly use the score as just for ranking purposes, but now it's better normalized, so you can actually use the scores to set a threshold. Like, for example, I only want to pass on results that are over 0.5 or something like that. And next. This is a great visualization of how the results will improve with numeric reasoning. So if you want to find standing desks that are shorter than 130 centimeters, here's an open source reranker on the left that it's just latching onto the idea of 130 centimeters and returning a lot of standing desks that are 130 centimeters. But reranker has that numeric reasoning, so it has all these results that are actually less than 130 centimeters with a sharp drop off after 130. Next, yep. So also date understanding. So between May and August, and you can just see that visually here. Previously, with other re-rankers, you would get May and August boosted because of those words showing up there. But now you have the concept of time in the model itself. So you have, and it understands that between May and August, that includes May and August. It picks up on very nuanced, if it said exclusive of, I would want to do that test, but I think it could understand that, and then not include May and August. And then even like very exact dates. So what flights do I have before April? So this, yeah, here's an example of exclusive of the date mentioned. So before implies not including April. So you can see on the right, it's returning results that are not part of April. So one last thing about that last slide, just think about your own applications. If you go back one slide, Arjun, if you're asking for results that are before April, you're getting good results from your hybrid search with your lexical, with your embedding search. You're getting some good results, some bad results. But then if you're applying a re-ranker that doesn't understand this, you're basically weeding out all the good results before passing it to your generative. So is really like just killing any chance of having a good result for this type of question if you're not using a re-ranker that has all of these reasoning capabilities. Yeah, okay. Demo time.
Woo! Also, before we hop into the demo, I wanted to share a simple diagram of what we're going to be showing. As we mentioned prior, we're going to be showing you how to implement semantic search over a financial data set. Specifically, we're going to be working with the 10Ks of Compaq, which was a computer company back in the 90s and earlier. We'll show you how to upsert and embed this data with integrated inference. We're just going to toss it at the endpoint that we're working with in Pinecone. And then we'll show you how to conduct semantic search, which will allow us to use an embedding model inside Pinecone, the Pinecone vector database, and Cohere, which has been the re-ranking model, which has been deployed on Pinecone infrastructure. And of course, we'll analyze the return documents and see how they differ when you use the re-ranking endpoint and when you don't use the re-ranking endpoint. All right, I'm gonna stop sharing my screen and transition into the notebook. By the way, thank you everybody for asking your wonderful questions. We will have a long Q&A time at the end of the webinar, and we will answer as many as we can. Please use the Q&A functionality so that we can keep track of who is asking what.
And when Arjun says long, he means long. We're not just saving 5 minutes at the end. We're gonna
Yeah.
do this demo in maybe 10 minutes tops, and then spend the remainder of the hour for questions. And we will be giving access to this notebook. Arjun, are we giving access to this right now or after the?
It will probably end up being shortly after.
Okay. So we'll
But
give
it will
access to
be
this afterwards, and with the free tier of Pinecone, you should be able to run through this.
all
Just remember
right.
those things down after.
All right, so here is our example notebook. In order to save us a little bit of time, I'm going to avoid running the data preprocessing and upsertion steps, but I'll still go through them and explain them to you all so you know what's going on. We're going to first start with a bunch of installs. Here we're installing Pinecone, some dependencies to help with API stuff, and Rich, which allows us to display these results in a really nice fashion. Jan, can you see everything good? I want to double check before I went
Yeah,
forward.
looks great. If anyone has trouble seeing, put it in the chat, but it looks good to me.
Awesome. We'll start with our imports. Again, a lot of these are to help with data preprocessing and to also help with displaying the results inside the notebook. So first, we're going to start by finding and grabbing these SEC documents. We've grabbed them from 1994 to 2002. Fortunately, they're available as text files directly from the SEC Edgar database. So we're just going to scrape those text files and download them inside this notebook. One thing to note is that if you run this notebook yourself, you have to declare your company and your email in the API call or in the text scraping call so that the SEC knows who's using the endpoints and what. So you'll get a little prompt here to declare your company and your email, and we'll download the files directly inside the notebook. If we look inside our folder there, we can see that they've downloaded. Then we'll just create this dictionary of text and year files so that we know what document was published in what year. The thing about working with these 10K documents in text format is that they actually have a lot of HTML and a lot of tags that we might not necessarily need when we're embedding these chunks. So we've written a few functions here that let us parse the text of the 10Ks, specifically allowing us to keep everything except the table, or keep everything, to throw away everything except for the table tags, which we're going to segment on further for later analysis. And also some of the text tags that we really care about. So some of the additional documentation we're not interested in, we just want the 10K proper. Then what we'll do is we'll take each given 10K and we'll chunk it based on whether it is a table or whether it is not a table. This lets us kind of cleanly pull out the tables from the 10Ks, since we're going to primarily focus our analysis on the text that's located inside the 10Ks. Although inside this notebook, we have left the 10K, the preprocessed tables as well. So if you like to copy the notebook and upsert the tables and interact with them, you can, but that's outside the scope of this example. You can see that an example of a 10K table looks like this. This is what we're going to be separating and pulling out on, because we might not be able to search over them as effectively as we would any other given text. We're going to parse the 10Ks, we're going to split on tables, and we're going to clean those cleaned texts so that we are chunking really neatly. Now, one thing that's really important before we start using Pinecone's integrated inference API is that we have to chunk the text. So I've written a really simple chunker that just chunks in terms of 1,500 characters. This is an arbitrary number just to fit within the context window of the embedding model that we're using, which is multilingual E5 large. You can make this larger or smaller. We haven't placed a big emphasis on what this number should be because we want to place importance on what the reranker can do for you outside of kind of tuning a chunking parameter. Then we'll chunk based on those texts. Next, the next couple of blocks help us set up Pinecone, checking whether we're inside Colab or whether we're not. And of course, in order to upsert into Pinecone, you'll need your API key. So if you're following along in this notebook, please make sure to go through the quick start and create an account first before you continue. And of course, you'll be able to use Pinecone for free under the free tier. We have to name our index reranking compact is the name we'll use, and we have to create our index. This is the first step in which we're interacting with the integrated inference endpoint. We're using pinecone.createIndex4model, which is different than just creating an index normally. In this case, we're specifying the model that we're using, which is relevant because the model has a dimension size for the embeddings that it produces. So we handle actually setting that query, feature for your index, in addition to some other parameters like the region and the cloud that you might be using. Finally, we need to transform our data into records in order to upsert in a really nice fashion. So what this is allowing us to do is upsert each data point as text chunks, and also adding metadata like what type of chunk it is, like whether it's text or table, and what year it was filed in case you want to do metadata filtering, which lets you kind of narrow down your search to a specific year if you decide to do that. Finally, we have this upsert in batches function, which kind of helps us hit the upsert records endpoint in order to avoid hitting rate limits. And in this case, we're doing batches of 96 because of the limit on the embedding model that's doing the embedding and the upsertion. At this point in the notebook, we've upserted all of our documents into the vector database, and we're free to query. So if we look at our index search records call, we specify our namespace, which is compact. We can pass in our query in this text field under inputs, risks to compact for dollar hedging, and we can also specify if we want to use a reranker, which we've done here, saying we want to use the Cohere rerank 3.5 endpoint. We can parse the results that are returned, and we get these chunks back, which refer to foreign exchange instruments and so on and so forth. We have a few more helper functions before we get into the actual re-ranking testing and results. And I want to also say that we're going to be showing you how to use each feature of the re-ranker that we've described already. So the temporal reasoning, the numeric reasoning, and the other forms of the negation reasoning, most importantly, how you can use that inside a query and what those results will look like. I've written a wrapper here to make it easy for us to just hit the database directly without specifying the key parameters each time. What we've done is that when we're not using the re-ranker, we're going to return 20 results and then just the first 3 of those 20. When we are using the re-ranker, we'll return 20 results and then re-rank to the top 3 so that we can see what the most relevant chunks are out of things that are being returned. Finally, like I said, we're using a package called rich in order to kind of display the tables in a really clean, nice fashion so that when we can compare what happens when you use the re-ranker and when you don't use the re-ranker, how the chunks differ in terms of their content and how high or low they are in the returned results. All right, I'm going to hand it over to Jan so he can explain exactly what the re-ranker is doing with each of the queries that we're working with. As a reminder, we're going to start with a simple query, and then we're going to expose different capabilities of reasoning that the Cohere re-ranker can handle in order to re-rank the results that are coming from the end. All yours, Jan.
All right. So Arjun is actually the in-house expert on compact by this point. I discovered Arjun reads very fast, so went through a lot of the Wikipedia to help come up with some of the most relevant questions that an analyst might ask. We chose compact since it's a bit more of a historical company at this point. So we had some fun with that. So here's a base query, and then we'll add reasoning on top of that base query. The first one is changes in Compact's product offerings and their impacts on sales. So I expect both of the models to do pretty well with this because it's just something that like a semantic reasoning, a semantic model, like an embedding model, should understand well. And we can see that the left side here, like the first full sentence, the company faces product transitions. So that's related to product offerings. And then the next sentence has uh, or increases of sales of newer PCs. So it does talk about products and sales. On the right side, in the first complete paragraph, it does talk about product transitions as well and impact on sales. I don't know, Arjun, do you have a preference between the left and the right here?
Yeah, it's hard to say because the query is so straightforward. What is interesting is that it seems to be grabbing maybe a repeated chunk that exists across multiple 10Ks. For example, there might be predictable structure inside the 10Ks where product transitions are talked about frequently. And on the right side, we've kind of grabbed the chunk that is a little easier to read, starting with the product transitions header, whereas on the left side, we're kind of jumping in the middle of the paragraph. I think when we look at the second chunk here, it starts to get particularly interesting because we see that the reranker is returning sales results, whereas the without using the reranker, we don't really get any mention of sales figures at all.
Yeah, and we were thinking about why that might be. And if you look at like 62% increase for a CPU product sales, that might look a bit more of a like meaningless number to embedding model or reranker that doesn't have numeric reasoning capabilities.
Exactly,
Um,
because of tokenization, because it might not be actually broken down or represented in a way that has any meaning.
right. Yep, that makes sense.
Let's go on to our second query here, in which we take the existing query and try to expose some of the numerical reasoning capabilities that the Cohere reranker has.
Right. So this is the same query, changes in complex product offerings and their impact on sales. But now we're getting more specific and saying, and show changes greater than 30% in sales. We want to make a report about the big events that happen. Now, let's ignore the things under 30%. So on the left side, I'm expecting to see either nothing with numbers or maybe an exact hit on 30%. So far, I'm not seeing numbers, so it's kind of just ignoring that, perhaps. Whereas on the right side, I immediately pick up on here 58% of sales. Um, and that already meets the requirement. And then you can also see the significant increase in sales um, gets broken down. So it meets the requirement.
And I want to clarify here that we're just showing a semantic search pipeline, and the performance of that pipeline is also dependent on how we're chunking the data. But what's interesting here is that this chunk was not as prioritized in our previous query. This was the second result that was returned. But now that we've added this condition, almost, we are now seeing it as the first result, whereas without the re-ranker, it seems like nothing has changed, or we got results that were not as relevant.
Right. And um, uh, although we're working on just search, just keep imagining how this might influence what you feed into the generative model. Oftentimes, a generative model will prioritize higher results. Plus, if you're only returning a certain number of results, you might be cutting out the actual valuable information.
Exactly. Like imagine you just cut off to the first result here. You wouldn't have any sales data at all. Just want to
Right.
make a quick note on this last chunk. We don't get any more sales data without re-ranking. But with re-ranking, we get some figures from 1993 as well, which include sales figures above 30%, which is also kind of cool.
So we get like two or three actual relevant results on the right and zero of what we want on the left. And then negation capabilities. So now we're going to move over to acquisitions. Thanks again to our historian Arjun for figuring out that acquisitions was an interesting part of complex history. So we're going to ask about their largest acquisitions. And already even though this is focused on negation, the concept of largest sort of is leaning on numeric reasoning capabilities because sometimes the concept of large and largest depends on how acquisitions are defined by their acquisition value. And then we're gonna, yeah, so let's start with just that base query, largest acquisitions in compact history. On the left, we see an acquisition with $359 million in cash and 22 million in cash. Um, so that's not as big as on the right side, where we're seeing a very tight summary of multiple big acquisitions. Um, does it mention the amount there?
Not in this first chunk. There's no amount information here. But what's interesting to note is the differences between what was retrieved. So on the right side, we see a lot of historical acquisitions that did end up being quite large, especially that of Digital Equipment Corporation, which at the time was huge. I think it was around $10 billion acquisition. And then on the left side, although we do see figures, they aren't necessarily of kind of what has happened over the long term, which the reranker has seemed to capture it on the right side. Of course,
Right.
we can't give it too much credit because there isn't any information about the amount of the acquisition within these chunks, but that's still something that is relevant to our query. What acquisitions happened and with who?
And you pointed out earlier when we were working on this, Arjun, the left side, the companies don't even have names. So maybe
Right.
you picked up on, okay, it's a named company and it must be bigger.
When we go onto the second chunk, we start seeing some information on like the actual acquisitions. So we see probably some document from 1998-ish about the acquisition of Digital Equipment Corporation, which happened in 98, and then an acquisition with Tandem, which happened in 97. And to the non-reranking endpoints credit, we start seeing some of these specific acquisitions that were quite large that were referenced in the earlier chunks.
Right. Yeah, 4.8 billion is more than 257 million.
Of course, we get the similar chunks again on the right side for the re-ranker, and on the left side, we actually we have description of another company that was acquired, but it seems to be out of context. It might be related to what products are being developed rather than the importance of the acquisition.
Okay, but what if I do not care about Digital Equipment Corporation because I've been hearing so much about it already? Let's focus on the other companies. So how do we get that out? Oh, one thing I meant to say earlier, by the way, is some type of these things you could do with metadata filtering, but a lot of things you might not have categorized like pre-processed well into your metadata. So this is really helpful to make up for any lack of data cleanliness. But yeah, let's look at not digital equipment corporation. So on the right side, I do not see it. On the left side, it immediately comes up because it just does not understand the concept of negation as a
Right
semantic.
here, Compaq announced the execution of agreement to acquire Digital Equipment Corporation. So that's an immediate X using without using the re-ranker. And just like Jan said, on the right side, we're actually getting all of the acquisitions after 1998, and Compaq was acquired in 1998. So it's kind of cool to see that it found a chunk that doesn't mention a digital equipment a corporation and return that chunk. It could have picked the same chunk that we saw prior, which mentioned all of the acquisitions, but it returned a chunk instead that didn't mention it.
Yeah, I mean, think back to a time when you were chatting with a chatbot or a RAG system, and you just ended up saying, no, 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 uppercase, I do not want this, and it just never understood the
Yeah.
negation.
Let's see what happens in the second chunk. So we get Digital Equipment Corporation again on the left side.
And again, not on the right, right? Nope.
Yeah, I don't think so because we have 99, 99, and that's it. And again, just to reiterate, we're not filtering, we haven't done any filtering on year. This is just purely based on the results that are being returned and how they're processed by the reranker. Finally, the third result, we do get mention of Digital Equipment Corporation with the reranker, but it's under the title of digital, which Digital Equipment Corporation also goes by.
Right.
And that can be a difficult edge case to handle because encoding the word digital to mean the specific entity, Digital Equipment Corporation, is probably very difficult to do unless you describe what that is, given how contextually these embeddings are created. But the fact that we got a pretty relevant result like right at the beginning is pretty impressive.
All right. And then I think this is the last one, right? Before we open up to Q&A. So it turns out 10Ks don't break it down a lot by quarters or by months. I wanted to show off some more granular data because you can just filter the years by like the file names, which have the years in them. But we decided let's keep this simple and pretend you cannot do metadata filtering here. So let's pretend the years are not in the files and just ask for consumer products that Compaq started selling in 1999 and beyond. And then not using the metadata, we are getting on the left side 1997, and that is before 1997. So on the right side, we're getting 2001, 2000, and 1999. So that's correct. And again, same thing here. We do get 2000 on the left, but we also get 1998. So again, a bit of a miss there.
And it's important to note that on the left side, we're not really talking about any products in specific, whereas on the right side, we're talking about product lines that Compaq had started selling or were selling in those years.
Nice. Okay. So, and similar results here. Shall we open it up to questions?
Yep, that's it for our demo. So why don't we go ahead and ask some questions, or answer some questions rather.
Awesome. So, let's go from the oldest going forward. So, so
Yeah, let's
Chris,
start. Oh, go ahead.
yeah, go ahead.
Yeah, so let's start with Crispin Courtenay's questions. Hi, Crispin. What about multi-embedding, which is using a different engine? I've seen a few white papers and examples on this, but I have no idea from a practical standpoint. So I will handle this because this sounds like kind of like a vector database question, and then Jan, you can answer from like the Cohere offering side. So we don't support embedding models yet. So this is the idea that I believe it's the idea where you have a given document, you might generate multiple embeddings like per chunk or something along those lines. You get to decide how you want to embed your data and upsort it into Pinecone. As long as you can represent your data as vectors and you've done whatever mapping you want on the metadata side, you can handle that on your own, but we don't have like specific support for some of these multi-embedding methodologies that I believe you're referencing. But as long as you can turn it into embeddings and as long as you can attach metadata to them, you can use them in Pinecone. We're very agnostic to the type of embeddings that you're actually putting in there.
Okay. And Davide, how do we choose the best re-ranker for a given application? So I've seen state-of-the-art results across all benchmarking categories for a re-ranker on Rerank 3.5. So and we've seen good results also in our customers abroad in various languages. So we've designed this to be quite a general purpose model. Uh, you can fine-tune re-rank, but most of the time customers do not need to fine-tune.
It can also depend on the specific qualities of the re-ranker that you're trying to use for whatever downstream task you're working on. So in this webinar, we exploited the fact that Cohere 3.5 is really good at numerical reasoning, which is super handy for financial domains. And of course, if you're working on some data set that might not need numerical reasoning, maybe you can still use Cohere 3.5 for a different attribute of why it's really performant, but you might have to look about what other attributes are relevant to you and your application.
Yeah. For applications where you have Like you always know exactly what you're searching for because you have like SMEs who are using it and you have a very well organized data set. Maybe you even only need lexical search. So there's a whole spectrum. Um, Go ahead.
Yep. So next question, also from Crispin. Thanks again. Can or should you use a graph database in some sort of re-ranking pattern? So from the Pinecone perspective, we don't support like graph databases specifically. We do have learn articles on how you can use graph databases in addition to Pinecone. So if you're looking at how to kind of combine those two resources, you can take a look there. I don't have any other contribution on whether graph databases can be used with re-ranking because I don't really work with them that often. Jan, do you have any perspective on that?
Yeah, any type of search can be used with re-ranking because it's just that last step after lexical search, after semantic search, after hybrid search, after graph plus semantic. So whatever search, you can still funnel it into re-rank as that final step before generative or just before displaying the results.
Next question from Chris. Chris, this is a great question. There are in our docs, in Pinecone docs, it says they're supporting embedding models. These are the ones that are hosted on Pinecone infrastructure. You can bring any embedding you want and upstart it directly into Pinecone using our upstart API. But if you don't want to deal with using another endpoint, or if you don't want to deal with using a third-party API model or deploying an embedding model yourself, then you can use the ones that we've handpicked on our infrastructure. And one of the models that we've handpicked is Cohere's rerank model, which you can just use inside Pinecone without having to make an explicit API call to Cohere. Hope that helps answer that question. Oh, recommendations on the best place to host a custom face, Hugging Face model to use in RAG. Really depends on what your stack looks like, where you are in the life cycle. If you're asking for me personally, I love using like modal on my personal projects when I need to do any sort of quick like serverless like inferencing stuff. But it really depends on what you're using. You could use AWS, whatever is like most helpful for what you're working on. Thanks again, Chris.
Yeah, coming from
Ah,
AWS, quick shout out to SageMaker Jumpstart makes it very
right.
easy to launch Hugging Face.
Oh, great question from anonymous attendee. Would it not increase the latency of results when we start to re-rank them? Yes, that is correct. Re-ranking will increase latency of results, but it will only increase them by a small amount. The nice part about having a deployed model on our infrastructure is that the inference time is still quite fast. I believe in our blog post we might have some figures on exactly what the latency should be. Jan, it would be great if you could share like maybe the speed increases from going from 3 to 3.5 or anything that you might know about there. But yes, it is strictly true that latency will increase. However, because it is on hosted infrastructure, the latency increase will be small. The amount of documents that you're passing will also increase the latency. So if you're passing like 100 documents or some large number, because you're doing all these pairwise computations, you're going to have to run the model on those. That will increase latency.
Yeah, if you give me a few minutes down the road, I can show some latency graphs. But in general, it's like in the order of hundreds of milliseconds or less. But it actually can reduce the overall latency of your application if you're having generative after the search results. So I'm talking about retrieval augmented generation, because the generative model is typically the bulkiest model in the pipeline. And if you can reduce the amount of context you're passing to the generative model, you can actually see like well, from a total cost of ownership, you can see like a 98% reduction of total cost of ownership of your RAG application just by introducing a re-ranker, because you're reducing from maybe like 50 or 30 or 20 results you're passing into the generative model. And basically, you're asking the generative model implicitly to do re-ranking, which it's not optimized to do. And by re-ranking the results first and just passing in three, or so, you can end up decreasing the latency of your RAG application.
Awesome. Just a quick note, everybody. If we don't get to your question, you can always ask them in the Pinecone community discourse, which is available on our website, or you could contact like myself or Jan directly. All right, let's do a little bit
Or
of
on the
a
Cohere community Discord if it's specific to Cohere.
yes. Let's do a little bit of a speed run. So Swapnil is asking about hybrid graph rag and whether Pinecone and Cohere have any applications for it. We do have a Learn article on our website on using graph rag with Pinecone, so I encourage you to check that one out. Does date understanding also work on numerical representations? Jan, could you handle that?
Yeah, it does. Like date understanding as in different formats of dates, right? Yep,
Yep.
that should work.
Does Sujit is asking if the re-ranking model has any preference on the underlying vector database? No, it does not. It's just the re-ranking endpoint. You could use the re-rank model directly from Cohere, for example. We have it hosted on our infrastructure to reduce the amount of API calls you're making and also make the inferencing faster if you're just using Pinecone.
And it's separate from the vector DB. So it's actually not taking any information like from the vector DB in a way. It's not getting the embeddings from the vector DB. It's getting the metadata from the vector DB in a way because it's passing the underlying text results, not the embedding results. So what the re-ranker is receiving is the text query and the text documents. It's not receiving any pre-embedded things.
Milos, you have a wonderful question on kind of pre-processing and adding filters for semantic search. So I'll just summarize quickly what you're saying. You're working on e-commerce data. You can compute metadata filters using some sort of LLM and then construct those filters and put them inside either the Pinecone call or the actual query. How can you use the re-ranker? Great question. It will save you an LLM call because theoretically it will have this understanding of like what those filters should look like. It'll save you any issues and hallucinations. So if you're trying to parse the filters in a really structured fashion and that generation fails, you won't be able to complete your search. Whereas with this querying, the search will go through because you're not doing any sort of underlying data transformation, and you'll be able to return results that are somewhat interesting and useful. The third benefit is probably that you don't need to know all of the entities that you need to parse in advance, which might be really difficult for an LLM to generalize, especially on a really specific domain. If you let the user specify those entities in natural language, the re-ranker can kind of understand what relationship those entities have with what logic needs to be returned in the re-ranker, and you can kind of circumvent doing that additional work. Does that cover all of those reasons? Jan, did I miss something there?
Oh, that sounds good.
Awesome.
So are there any papers or other explanations for why the re-ranker is better? I don't think we've released that. Is there a numeric metric to compare the results generated from different models, specifically for RAG outputs? Um, there's uh, there's many ways to do it. You could use like a judge model, generative model to compare them. And do you have any thoughts, Andrew?
Um, it depends on what there's a lot of viewpoints on evaluation for a given thing that you're trying to do. It depends on what metrics matter to you. So you could have a really simple metric of just like, okay, of the return chunks, how many actually answer the question and how many don't? And you can use that as your estimate as you're going forward. It really depends on what you're trying to do and how you can abstract that. Very often, a lot of the metrics that other people use are like either generated with an LLM or they're heuristics based on like word overlap between the query and the document. And all that stuff only matters if it matters to your use case specifically. I'm a current Pinecone customer, use Voyage AI for embeddings. Can I use Rerank? Absolutely. Just to clarify for everyone, the way the rerank endpoint works is that it takes the text query that's returned and the text documents which are stored inside the vector database and recomputes their relevance scores on a pairwise basis with every query and every document. So it doesn't care about what the embedding model was used for whatever preceded that step. It's going to reprocess the data through the through the re-rank model and compute those scores again. So you can use any re-rank endpoint with any embedding model. You don't have to do anything here. And if you specifically, Joanza, want to do what you're describing, which is using Voyage AI and use re-rank, you can just call the re-rank model via Pinecone inference, which lets you do the specific re-ranking yourself.
Is
Ooh,
there
great example of score normalization. Yeah, go ahead. This will be fun.
Yeah. We have normalized it so that it's not hovering around 1 or 0 anymore. And you can filter it like above 0.5 or so. Arjun, I think you wanted to say something about that.
Oh, just that uh, the reason why score normalization is important is because with some re-rankers you have saturation. So because
Right.
you're predicting whether something is relevant or not, like you might saturate a result to be like 95, 95, 95, 0.1, 0.1, 0.1,
Exactly.
and then it's not really that interpretable because you're predicting whether it's 1, 0, relevant, not relevant, and then you're kind of doing probability scores, which like kind of saturate out. But what Cohere has done is like actually made those scores spread out more so you can do that more fine-grained like ranking or ordering.
Exactly. Well said. What have you found for best practices for soft filtering dates, titles, etc.? Yeah, a soft filtering, I assume you mean like as opposed to using metadata. Yeah, so um, it we've built it to be pretty resilient to many different ways of querying. I think the tricky part was just like whether the answers even exist in the documents or not. But if you're asking the right questions, I mean, because it exists in the data, it's pretty flexible. Is Rerank optimized for all sorts of documents or especially for finance documents? It's optimized for many use cases. So we have internal benchmarks where we're doing like uh, state of the art for project management, hospitality, e-commerce, and like yeah, all kinds of industries. What is the cost implication to use Cohere Reranker model? So you can see that on the Pinecone pricing page, right? There's per token pricing. It's quite minimal. Who are your competitors in providing re-ranker models? A lot of folks use open source models. Someone mentioned Voyage here. Um, how well the embedding handle contents in big tables or big Excel or CSV files? Um, oh, that's a question for you, I guess.
Yeah, so many embedding models can't support like tables natively. You'll have to use one that has been trained on tabular data, which is why we kind of excluded the tables from this demo. So it depends on the embedding model that you're using. The one that we were using, multilingual E5 large, can't necessarily do that on the fly. I think we are just at time. If anyone has any more questions, feel free to contact me directly via like LinkedIn, or you can contact us via the forum. Jan, where can people find you or Cohere if they need help?
You can find me on LinkedIn via my name, and you can also email me at my first name at cohere.com. And you can also find Cohere on Discord.
Awesome. Thanks again, everyone. This was great. The notebook will be uploaded shortly underneath our GitHub Pinecone examples, so we'll send a link out once that's there. Thank you all for coming.
Thank you all.